So let's take a look in general at basicity, understand what will support the basic properties of the compounds, and then we will look at nitrogen bases. So if we think about bases in organic chemistry, a basic compound should have an ability to pick an acidic proton and then keep it on and not let it go, okay? So, and since in this chapter we are talking about amines, we're going to look at amines as potential bases. And what we know about amines is that in a neutral amine, we have nitrogen with 3 bonds and a lone pair of electrons. And it's that lone pair of electrons that will be able to obstruct an acidic proton and form a conjugate acid. And here in this example, I put our well-known base that we've used so many times already. That's triethylamine. So if we think about what makes triethylamine such a wonderful base, base should have electron density to share. It does have that electron density available in the form of lone pair of electrons. To enhance it, we need to push electron density towards the nitrogen. And with hyperconjugation from adjacent alkyl groups, which are representing field sigma bonds or field sp3 hybridized orbitals forming sigma bonds on adjacent positions, we understand that electron density will be repelled. And so your alkyl groups will be pushing more electron density towards nitrogen, making it more electron negative and capable of bonding to that acidic proton. So we understand that in this case, the favorable effect will be hyperconjugation. And hyperconjugation will be favorable in this case. And once we have the proton attached to the nitrogen, in that case, how this triethyl ammonium ion will be keeping that proton, the ethyl groups will close up around that proton, making a little cage for it. So in reality, what is happening, and I'll give you a cartoon of that, when you have your free amino group, so there is not too much repulsion from ethyl groups, they will turn away from the lone pair of electrons on nitrogen. So they will support the lone pair density on the nitrogen, but at the same time, keep away so they will not be causing too much steric hindrance. When proton is attached, my nitrogen will pick the proton by using its lone pair of electrons, so it gets a positive charge. And now, because my nitrogen has a positive charge on, but basically it's hydrogen with very little of electron density, those ethyl groups are going to turn towards the hydrogen, trying to give that empty orbital some electron density. So now we went into a cage mode. Caging of proton, and that's beautiful. So originally, those groups are away, less steric hindrance. to nitrogen. And that's what we want for basicity. And when we form a conjugate acid, we want that proton to be caged between those alkyl groups. So that's why your triethylamine is a wonderful, wonderful base. The other base that we talked about so many times, and very often I would tell you, guys, you can use either pyridine or triethylamine, is pyridine. And in the molecule of pyridine, we already went through chapter 16. It's our heterocyclic compound. Nitrogen is included into 6-membered ring. We've learned already that the lone pair of electrons on nitrogen does not reside in the resonance delocalized circle within the 6-membered ring. So if we draw this compound sideways, the lone pair of electrons is residing on sp2 hybridized orbital, and it's not a part of the resonance delocalization. So here, my nitrogen is less hindered than in T. So in the beginning, you're saying that, well, it's much, much better than your T. But once the reaction is complete, and again, I'll simplify it, and you form your pyridinium salt, think of it, your proton is residing within the plane of the molecule, and there is nothing to protect it from stealing back with the conjugate base. So we see no caging of the proton. So original amount of electron density on nitrogen is better, but capability of keeping that proton is not. And this is why those two bases, having very different sources of electron density on nitrogen, are going to give us almost the same strength as a base. So in pyridine, we can also see that the electron density can be delocalized by giving a resonance structure where nitrogen will acquire a negative charge, please understand that that extra lone pair of electrons on your nitrogen is actually going to be perpendicular to the ones that you originally had. So think of electron density delocalization. Oops, sorry, guys. Electron density delocalization, that's where those electrons will reside. So not the same plane where your original electrons were, but now we have even more repulsion towards nitrogen, so it will improve the amount of electron density on the nitrogen. So resonance towards the nitrogen does help. And on the other hand, if nitrogen will be losing electron density through induction or through resonance away from it, that is going to be unfavorable effect for basicity. So let me show you a couple of examples. So if I look at this example, the electron density is going to be taken from nitrogen, and it will resonate and resonate all the way away onto the oxygen. So we'll put a positive charge on nitrogen. My base is gone. A negative charge on oxygen, and that is not going to act as a base. So I've lost the basic properties. Unfavorable resonance away from nitrogen. Okay. Weaker unfavorable effect will be inductive effect. So let's take a look at an example here. If I compare this base with this one, A and B, my base A will be stronger than B. And the reason behind that is because in base B, this carbon is pretty electron positive because the inductive effect from fluorine pulling electron density away. And as a result, the lone pair of electrons on nitrogen will be pulled temporarily to improve the electron density on that electrophilic carbon. So the inductive effect again will be unfavorable inductive effect. Okay. And the more electronegative is the atom, the weaker is the base, and the closer is that electronegative atom to your amino group, the weaker is the base as well. So that much information, I hope, should be good enough for us so we can go into the actual problem here. Okay. So I'm going to quickly select this page, copy it, done, and then done. And then paste page. And oops. Let's move it over here and close it. So with that in mind, I'm going to quickly erase what I have down here. I have it on the other page. I'll post the notes and the recording for you guys. But let's take a good look at the problems that we are given on this exam. So we have a compound. When taken on an empty stomach right before Chem 106 exam 3, compound shown below produces side effects such as loss of common sense and unreasonable doubts. I think you have those side effects during the exam all the time. So arrange the nitrogen of this compound in the order of decreasing basicity. So let's take a look at our basic components here. Actually, you are directed to those. So nitrogen here, and this nitrogen. And let's see what we can expect from these nitrogens being basic under given circumstances. Let's put the lone pairs of electrons on. I'm going to start with A. So when I look at compound A, my nitrogen at first point of attachment to it doesn't have anything that can resonate towards or force towards nitrogen, or we could resonate electron density away from the nitrogen. So there is no resonance involved in this case. What we have as a point of involvement is inductive effect withdrawing electron density towards carbonyl here, inductive effect withdrawing electron density towards oxygen here. So we have two inductions of electron density from the nitrogen, and we have also a weak hyperconjugation towards nitrogen from the alkyl group. So here, no resonance contribution towards it. When I'm looking at base B, what I see here is that adjacent to my nitrogen, there is a double bond that is conjugated all the way to the carbonyl. So in this case, the electron density will be taken away from nitrogen by resonance away from the original position, giving me the negative charge on oxygen and positive charge on my nitrogen. And that will disable my base. On A, I don't ever get a full positive charge on the nitrogen. And finally, for base C, we have double bond towards the nitrogen, and it already tells me that if I get a resonance, it's going to resonate towards the nitrogen and not away from it. And the resonance can be extended by picking the electrons from the oxygen and then extending the conjugation all the way to the nitrogen, in which case my nitrogen will get negative charge. Oxygen here is getting a positive charge. What I want from my base to have as much electron density as possible. So when arranging my compounds in the order of decreasing basicity, we can clearly see that the best base here with the added electron density on nitrogen will be base C. And then it's going to be between A and B. It's going to be A because nitrogen will never get a formal positive charge, and then it's B, okay? We're asked to justify the choice for the least basic nitrogen. More than words will be needed. Please don't write an essay for me for justification. The actual structural justification is much, much better. And because I already showed the resonance towards the oxygen, what I will do here to save myself some time, I will just put a resonance arrow and I will draw this fragment with delocalization of electron density. I'm going to just do this over here. I'm allowed to do that because I'm really not interested in the rest of the structure. So let's see. We've moved on electrons here, 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 and over here. Nitrogen gets a formal positive charge. And as we can see here, basicity is disabled. And that is our justification. If you guys know. Yes.
I wanted to know why for C it didn't resonate towards the oxygen like how it did in B.
Okay, so Liana, let's just take that nitrogen. Okay, I'm not gonna draw the rest of the structure. Just that much, okay, because that should be more than enough. Let's try to resonate the electrons from the nitrogen. Let's try doing that. This carbon has a hydrogen on, right? When I do this, off of it, the only way I could resonate onto this position is if on adjacent position I had a double bond. So I could resonate the electrons, but I don't, okay? So by resonating electrons over here, I'm affecting this carbon. It's already overbound, 5 bonds on it. So it will break this bond or this bond, and it's a sigma bond. It's no for resonance delocalization. If I go this way, my nitrogen, I will have 1 bond here. This will be positively charged. The nitrogen will get an extra lone pair of electrons, will get a negative charge. I have incomplete octet, but it's still keeping my entire structure intact, and I do not lose the structural identity of the compound, okay? And I, of course, now I can move electrons from oxygen onto this position.
Okay, thank you.
Did it make sense, Liana?
Yeah, it makes sense. Thank you.
Okay. Other questions?
Yeah, just something to kind of clarify is, so the reason that, let's say, like B, we don't want a positive charge on the nitrogen, right? So that would be more of a factor of the disabling of basicity rather than the negative charge on the oxygen.
Yeah, absolutely. It could move, you could move the electrons if instead of, good question, Rita, if I didn't have oxygen here, it was just carbon to carbon double bond, you have a pool of electron density for conjugation. So you would get a negative charge on carbon. Anyways, it will go away. The fact is that the electron density is going away from it, and it's going away through resonance.
Okay, thank you.
Absolutely. Okay, so now we're ready for the next page. If you guys have questions, please ask. If not, I'll move on. We're good? Okay. I'm going to cover this problem here. We've talked about it today, so it's a really great example of looking at the differences between Hofmann and Koppe elimination. So this problem states that compound below goes through Hofmann and Koppe elimination reactions at drastically different rates. Choose the fastest reaction and justify your choice. Provide reaction conditions, write a detailed mechanism, and circle the major product for the fastest reaction. But before I can make my conclusion, which reaction will be faster, let's make sure that for each reaction, we put the proper conditions so we don't forget what will be happening there if that's the fast reaction. For Hofmann elimination, the conditions were, first, excess of metal iodide, right? And second, we were using silver oxide, water, heat. For Koppe elimination, we do have, actually, let's identify our amine. It's a tertiary amine. For Koppe elimination, tertiary amine is suitable. So we have peroxy acid and some DCM and some added heat, okay? For Hofmann elimination, we have a cyclic compound. My expectation is that I should have my amino group being axial And the removal of the other hydrogen will be anti-periplanar. Okay. And for our coelimination, I will have to make sure that I have a syn elimination product. I actually do not want to have axial amino group on. So let's see how my compound will present itself before the reaction in most stable conformation. I have a T-butyl group on, so let's just draw the molecule in which T-butyl group will be equatorial. So if I wanted to go equatorially down, actually let me draw a right chair. Because it will be easier to present that equatorial T-butyl group. I could choose any carbon that is pointing up. So I'm going to choose this carbon. And 1, 2, 3, 4, 5, and 6, going counterclockwise. Clockwise, 1, 2, 3, 4, 5, and 6. Let's put the substituents on. What do I have? On position number 3, I have ethyl group pointing down. It will point down equatorially. On position number 4, I have my amino group pointing up, and it's going to point up equatorially. And finally, on position number 5, I have isopropyl group, and it's pointing up, and it's going to point up axially. This is my most stable conformation. We can see that out of 4 substituents, 3 are equatorial. And by just evaluation of my stable conformer, which reaction will go faster? Huffman or Cope elimination reaction?
Would it be the Cope elimination, since here the most stable conformer, the amino group is not axial, it's equatorial.
Indeed. So it is the fast reaction. So we're going to proceed with this one. We're going to leave Huffman elimination out of picture. So in this reaction, let's put the mechanism out. Let's choose any peroxy acid. Okay. Let's attack this oxygen, make a double bond here, pick up this proton, put electrons back onto this oxygen, okay? And we are going to have byproduct forming. Okay. Now remember, in Cope elimination reaction, I'm going to form a 5-membered ring. One of the bonds that I expect to form as a double bond is going to be either pink one or the green one. So when looking at the position of our leaving group and base at the same time, what I can see here that to obstruct a proton, let me put a little number in here, 1, 2, 3, 4, and 5. It's hydrogen A that is going to be in close proximity to the oxygen. So I have to be very careful about the choice of the hydrogens that will be obstructed. Those two groups, hydrogen A and oxygen, are syn to each other. So we're going to obstruct that proton, form a double bond, and the leaving group will leave. And the result of the reaction will be formation of water molecule, will be formation of hydroxyl dimethylamine, and we will form the product in which the double bond will be formed between the original position. Let me go to top view, original position of my amino group and the ethyl. So this is where I will be forming the double bond. So we can just redraw the product in the top view. That is it. That is your major product of the reaction.
So Miss O, in this example, we're choosing to remove HA not because that carbon is less hindered, but just because it's closer to the oxygen.
Mhm.
Okay, thank you.
Because, good question again. Let's take a look at our hydrogen B. We understand that there will be free rotation around carbon to nitrogen bond, but no matter how you rotate, if your oxygen ended up here, it still will be pretty far away from HB, right? So it won't be able to pick it up, but over here, they're on the same side of the double bonds that is going to go through formation of, through to the bonds that is going to be a double bond, okay? And that will be it. If my amino group were on a dash, then our expectation would be that we will be forming Huffman's product, okay? Do you want me to make an example, show it here, how the Huffman product will be formed? Yeah, okay.
Yeah.
And you guys, because I don't have a good memory, will remind me which group was on a dash, which on a wedge, so I will have some visuals of it. I'm gonna open a page, just don't want to make up something completely different here, so you will have a good comparison. I believe your T-butyl was on a dash, ethyl was on a dash, and now we're going to put this guy on a dash as well, okay? If we were given this molecule. Is that what we had?
Yeah, we were given it in a wedge, but since
Yeah.
we're changing it, yeah.
We're changing. Oh, I still have some memory. That's good to know. Okay, so now in this case, again, I want to start with the most stable conformer, and with T-butyl group going equatorially down, going clockwise, 1, 2, 3 on position number 3. I have my ethyl group equatorially down. I have my amino group, methyl amino group, pointing down. So now it's going to be axial, okay? And then we have isopropyl group being axial as well, okay? So what will happen in this case, now we have around our leaving group 2 positions, okay? One of which will be carrying hydrogen anti-periplanar to your leaving group, and the other one will be carrying hydrogen B. Oh, wrong direction. Hydrogen B. And it's not available for picking it up. So in this case, I have a good setting for Huffman elimination. Quick SN2 reaction. Step 2, hydroxy group will pick up the proton. Oops. And this group leaves. You guys can see that if we've changed the spatial arrangement of that one group, we still will be getting the same product as we've got in the previous case. But it will be for a different reason, and the product will be forming preferably by Huffman elimination. Okay. In this case, we had to choose hydrogen A, which was anti-periplanar to my leaving group. All good? So that T-butyl group is kind of a blessing to have if you remember that this is the first one that you are going to kind of balance out before you put the rest of the substituents. A very common mistake, guys, when the students put the top view into chair conformation, they do not draw the same molecule. What you really need to remember is that if you start with, let's say, T-butyl group on this position, you've got to see to make sure that if here you are putting your substituents on that ring in the clockwise direction, going 1, 2, 3, 4, 5, and 6, on your chair conformation, once you've positioned your T-butyl group on carbon number 1, you need to go around it in clockwise direction again. Because if you don't, you're going to have a completely different molecule, because if you go in this direction, you will be putting your isopropyl group on this carbon, and that's not where it belongs. Your ethyl is not here. And I see this mistake over and over too many times. Okay, let's move on. This one is another really neat problem. Sometimes I get so upset at myself that I give you all the old exams and my creativity is not giving me better examples, but let's take a look at this example. We're given reaction conditions, substrate and product. We're asked to draw the mechanism for the reaction. So let's go over it quickly. So anytime when all the information is given, you want to find the resemblance between starting material and the product. So let's do our quick investigation first and recognize what we have in the starting material. Well, over here, we have 2 cyclohexane rings fused together through a bond. So we're going to recognize those 2 rings by, I'm going to paint them in different colors because I want to see the substituents that are residing on them. So on my green ring, what I have, 1 carbon away from fused position. On this one, I have a metal group. And I have a carbon that is carrying an amino group. Okay. On the other blue carbon, 1 carbon away, I have a metal group. And then I have 1 carbon away, I have an acyl chloride functional group. So by just looking at this setting, I can see that on the green ring, I have a nucleophile. And on the blue ring, I have my electrophile. Electrophilic and nucleophilic atoms are being identified. Now, let's take a look at reaction conditions. I have pyridine and DCM. Definitely, I'm going to run an amidation reaction between my acyl chloride and amino group. It's the reaction within the same molecule. So I'm going to form, through intramolecular reaction, a ring. Let's take a look at the size of that ring. So if I number the atoms here, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and 6. Oh, sorry, guys. Sorry, I didn't count my nitrogen. 1, 2, 3, 4, 5, 6, and 7. Well, it looks like I will be forming a 7-membered ring and I would be forming an amide. When I look at my product, what I can see in the product is that I have 3 6-membered ring. So even if I form a 7-membered ring, somehow I would have to shrink it into a 6-membered ring. So what is that somehow coming from? When I look at my second step, I have sodium hydroxide, bromine. Let's add some water to it. And this reaction is the Huffman rearrangement reaction in which carbonyl is gone. And if my carbonyl is gone, I'm going to have a 6-membered ring in there with the amino group. So it looks like my story is adding up. But now with 3 rings instead of 2, I really need to see my starting material in the product. So my green ring, and this is how I would start my analysis for the product. My green ring carried at this position a metal group, and 1 carbon away, I had an amino group. So if I look at this compound, I see that out of 3 rings, this ring is carrying away from the fused position. It's carrying metal group, and then 1 carbon away, 2 metal groups, and amino group. Do you guys see this? Let me repeat. comparing these 3 rings, on this ring over here, what I see is that there is a carbon which carries a metal group, just like here. And then that carbon carries 1 carbon away, 1 carbon away, 2 metal groups, just like there, and the amino group. So that is my green ring. So I better paint it before I forgot. Do we see it now? Here we are. And so then I need to find the blue ring. And on my blue ring, I had a metal group as well. And so when I look at my compound, I can easily recognize that my blue ring will be this one. Because again, if I point at this position, it carries a metal group. And indeed, it does carry a metal group on. So now my original rings are being recognized, and I can see that I have to run the mechanism for both steps around there. All good? All I did, I just took drew the molecule in ChemDraw and rotated it a little bit just to confuse you, okay? But if you do your analysis, you won't be confused. So now we're ready to continue with the mechanism for step 1. And I'm going to just pick up that molecule and go from there. Let's put lone pair of electrons on nitrogen on, okay? And attack the carbonyl carbon. Double bond to oxygen will open up. You see what I did? I rotated my amino group closer to the carbonyl, so it's easier for me to draw my 7-membered ring. Okay, CH3 over here, and I'm not putting CH3s on anymore. I really don't have to. Just paint our rings, okay? So now we're going to close the double bond back on, kick out chlorine. I think I'm going to do this so it's easier for you to observe, guys. Let me put, doesn't look pretty, so let me prettify the structure just a bit. Okay, so now my nitrogen is still protonated, so I'm going to bring in pyridine. That's a good base. Abstract that extra proton. Return the electrons onto nitrogen. Don't forget to put your byproducts, guys. We're not going to utilize them any further, but we want to make sure that we keep track of all our carbons. Okay, this is the product for step 1. Now for step 2, the reaction is done with treating our product for step 1 with sodium hydroxide and then bromine. I'm going to continue right from there. Step 2. First, we're going to add sodium hydroxide to deprotonate our nitrogen. It's Huffman's rearrangement reaction. Okay. Now nitrogen will pick up on bromine, which is temporarily polarized. Okay. Moving on. So let's continue drawing our product. Now my nitrogen is carrying bromine. Let's move electrons through resonance delocalization onto the oxygen. This one is just a resonance delocalized structure, so there is no reaction there. Okay, almost home. So next step, this is where rearrangement will take place. Let me just take a second to make sure we're painting our rings so we don't lose track of what is happening here. I want you to have the good visual here. Bond from your lone pair of electrons from oxygen is going to move down. And instead of electrons resonating back on the nitrogen from carbon to nitrogen bond, this bond is going to break, will attach to nitrogen, and bromine will be kicked out. Nitrogen. So, and we're going to have double bond from that nitrogen to the oxygen, a carbon and the oxygen. Okay, we're almost ready to kick out that carbonyl group. We can proceed with just hydroxy group being there. That's fine too. So if I use hydroxy group and attack the carbonyl carbon, double bond to nitrogen will open up. Electrons will go onto nitrogen. And now we finally have our new 6-membered ring formed. Okay. So if we want to proceed from here, one thing that we can do is to close this double bond into double bond, move electrons from here onto the nitrogen. We will produce protonated carbon dioxide. Your nitrogen will have extra pair of electrons. It can pick up the proton from your carbon dioxide. And we will form the final product. Okay, so in the final product, let's make sure that we are presenting all of our rings properly. So our new ring is this one, and we started to form it from the beginning, but the 6-membered ring was formed in this step right here. And that's it. Okay. This is actually a pretty neat problem. If we decided to go with water instead of hydroxy anion, then we would attack with water molecule this position. We will have OH2 here, positive charge, and then we would do a proton shift, move the hydrogen onto this position, and then just break off the carbon dioxide. Either mechanism is just fine. Okay. I hope you guys can see how color really helps to put the project together, because without identifying the structural pieces, it will be very difficult to go through a problem like this. Okay, let's move on. We have a couple of more problems to solve. These are predict the product, predict the reaction conditions types of problems. So let's quickly go over those. We're given the reaction conditions. We're given the substrate. In the substrate, we're recognizing our functional group. It's an amino group. We have a primary amine. The reaction conditions with excess metal iodide and silver oxide are the Hofmann elimination conditions. I'm going to go through E2 reaction. I will be removing proton from the less substituted site. And I will be forming the most stable alkene, which will be a transalkene. So the bond will be formed between carbon-carrying amino group and adjacent less substituted carbon. So we will be forming a trans alkene here. Okay. Let's take a look at the second reaction. Reaction conditions are not given. So my job is to recognize the substrate in the product. When I look at my substrate, I want to have good visuals so I can easily track it down. So right from the beginning, when I take a glance at my reaction B, I can see that the big substituent, the tosyl substituent is gone. So, and tosyl is a great leaving group. So what I have as a skeleton of the substrate, my isopropyl group, I'm going to go off of it, and 1, 2, and 3 carbons next to it. When I look at the product, this is a good leaving group. It's residing on the primary position. Okay. 1, 2, 3, 4, 5 carbons in the main chain in the substrate. I go for the product. The product is flipped. 1, 2, 3, 4, 5. This part belongs to the substrate carbon chain. And I can see that through the reaction, I've added an extra carbon. And I formed a primary amine. So addition of extra carbon tells me that I had the nucleophilic substitution reaction with a cyanide, and then I went through reduction with lithium aluminum hydride. So let's put out the reaction conditions. I have a great leaving group there. So my first step will be addition of potassium cyanide. I'll use polar aprotic solvent, no heat. I can actually use DMSO. It's a killer reaction, would kill you if it gets on your skin or you will ingest it. Second step, we'll be adding excess lithium aluminum hydride in THF. And third step, I will be protonating the product, or instead I could use methanol. Okay. You can see counting the atoms does make a difference. So this is where your nitrile resides. Let's take a look at the next reaction. In the next reaction, again, I need to predict the reaction conditions. In the substrate, I start with aniline, good electron donating group, great electron donating group. In the product, I'm adding nitro group onto ortho position next to the amino group. And I know that sterically, that's not the best position to add. So what I need to do is to protect the para position first. So in the first step here, I would put a protecting group, sulfonate the compound. That's my fuming sulfuric acid. Second step, and let's put that product here so you guys will be able to see it. In the second step, I'm going to add nitric acid, catalyzed with sulfuric acid. Now we will be putting the substituent onto ortho position. And since in the final product, my sulfonate is gone. So I'm going to use dilute sulfuric acid to remove that group. Okay. Let's take a look at the last two reactions here. So we have, again, need to predict the product of the reaction conditions. I have abbreviated substituents on. I want to secure my safety and actually put the structure in. So let me erase this. I had benzyl here and I have phenyl here. I'm going to put the actual structures. So, oops, let me get rid of the white color here. Okay. So instead of benzyl, I'm going to put the actual group, and let me just highlight it. That's your benzyl. And now I can see that in the substrate, I have 1, 2, 3 carbons carrying a benzene ring and good leaving group. And in the product, I had phenyl group here. So this is where my phenyl group resides. And if again, I do the numbering here, I can see that through the reaction, I have the same number of carbons and my leaving group is gone and it's substituted with amino group. I know that I'm not going to just add an amino group to it because I will have polyalkylation. I also know that this particular reaction set, sodium azide and THF, will give me, let's put the product out. Will give me, SN2 type of reaction. And in the second and third steps, I'm going to add excess of La. And then followed by acidic conditions. No carbons are added here. I have 3 more reactions. Give me just a second, guys. I will be right back. Just a quick second. Let me pause the record. Okay, guys, just 3 more reactions and it will be done. So let's take a look at the next one. This one is kind of twisted. So what we have here, we need to predict the outcome of the reaction. When I look at the substrate, I see that my substrate is kind of a double-headed Gabriel reagent. I have available protected nitrogens on 2 sides of this reagent. If you guys remember, Gabriel reagent had just an aromatic ring with succinamide on it. Here I have the second group attached across the first one. Okay, so my reagent, my added reagents are potassium hydroxide, which will deprotonate my nitrogens. Okay, and then on the alkyl halide, I have a whole bunch of leaving groups. So here my goal is to do the following. I want to determine if I have some of the groups unavailable for substitution. And I also want to see if I could react both of these positions or just one of this in the substrate, these two positions are identical. So I'm going to move on to my reagent. And what I see here, if you guys remember in Gabriel synthesis reaction, once we deprotonated the nitrogen, we would have an SN2 reaction, which is the best for the primary positions, and then secondary, and then it doesn't work on the tertiaries. So when I go through my reagent, I have a primary position here with chlorine as a leaving group. I have secondary position here with chlorine as a leaving group. I have primary position here with iodine as a leaving group. And I have fluorine, bad leaving group. There will be no reaction here at all. And then I have tertiary carbon, and there will be no reaction on the tertiary carbon. So from available 3 positions and 2 nucleophilic position there, I'm going to exclude the ones that is not the best. Which one would you guys take away from possible reactivity?
The chlorine with the secondary carbon.
Chlorine with the secondary carbon. So this one is out of picture as well. So now we're looking at chlorine as a leaving group, iodine as a leaving group. Iodine as a leaving group is much, much better, right? So we are going to react this position, okay? And we would get one product on one side. Let's see if it will be possible to stretch our substrate on top of the Gabriel reagent and reach the other nitrogen as well. So I'm going to do this. I'm going to place my, oops, let me use the laser pointer. I'm going to place my benzene ring. I'm going to ignore this position and this position completely. So meta to each other, I have chlorine and iodine leaving groups, okay? So let's do this. On top of my Gabriel reagent, I'm putting my substrate. It has iodine here, okay? And once I form it on this position, it's going to turn away from the rest of the molecule. So even though I have an additional position with chlorine there, it won't be able to reach over it, okay? Because once the reaction happens here, I will get the ring on this side, and it will be very difficult for me to now reach over this position. So one of them is going to be unreacted. And once the reaction is complete and all gone, and I added my alkyl halide onto this position, this whole portion of the molecule is going to come off, and I will be left with this as a product. Let's see. This is still there. This is still there. And this is still here. And on this position, I will have NH2 forming. Now, guys, I want to extend it a little bit further. If I had the second equivalent of potassium hydroxide added and more hydrogen added, then this product would be able to react with this side of the molecule. And then this position will be available. So I would be getting an NH2 here as well. So think of it as if you had this as a substrate, and to that you would add 2 equivalents of your Gabriel reagent. Okay? Under basic conditions. This reaction will, or this position will react, and this position will react. Okay. Let's move on. The last 2 reactions. Here we have Huffman rearrangement reaction for problem F. In Huffman rearrangement reaction, a really important thing to remember is that your amide should be primary or secondary. And since in this case we have intramolecular reactions, I should be able to form a stable 5 or 6 membered ring. So let's see our positions with amides, 1, and then 2, and then 3. Right away, which position will we exclude from reacting?
The blue one, because it's tertiary.
The blue one is tertiary. Thank you, Susie. No reaction. And so I'm going to keep it as my backbone for the product because nothing is happening around there. And now see what will happen to the rest of the rings there. So let's just paint this blue. That's the one in the middle. Okay. On the left-hand side, I see that I have a 6-membered ring, so I can shrink that 6-membered ring. Remember, Huffman rearrangement, we'll lose the carbonyl, and we're going to form a bond between nitrogen and the carbon on the other side. So we will be forming a 5-membered ring over here. And that will be your small 5-membered ring. And on the other side, although we have a secondary amide, however, we won't be able to form the product because here, this will give you a 4-membered ring. This is a 5-membered ring. This stays 6. 6, 5. 4-membered ring is not going to voluntarily form. So we're going to keep this unchanged. Okay. The size of the ring and then the availability of 1 proton on your amide nitrogen. And only the last product here, the last reaction here, again, we're predicting the reaction conditions. Tracing is very important. So in the substrate, I see that I have a diethiene. And in diethiene, my reactive carbon is this carbon. It's already fully functionalized with 2 ethyl groups. in the product, my diethyine group is gone. And instead, I have an amino group added to it. So let's take a look at my product and see if we can trace the substrate there. I have a carbon carrying 2 ethyl groups. Here it is. My diethyine group is gone, and I am putting an amino group on. It looks like reductive amination at the end. So I need to recover carbonyl on reactive carbon. For that, my step 1 will be catalytic hydration in the presence of acid catalyzed hydration in the presence of mercury chloride. And once the ketone is formed, we're going to react it with the secondary amine. Okay. And for step number 2, I'm going to put it here aside. We will be forming an enamine. And then to fully reduce the product, we're going to use catalytic hydrogenation over palladium catalyst. And it's done. So your nitrogen comes with its ethyl groups. There you are. Your substrate came with its 2 ethyl groups around the reactive carbon. And that will hopefully give you a good visualization of the product. So the rest of the reactions we have not covered yet. It's from chapters 20 and 21. So we're going to leave it for some other time. I am done with whatever I wanted to cover today, guys. I'm going to stay for another half an hour to see if you have any questions for your upcoming exam. And I guess I will be making your exam tonight. Let's